Thank you. All right. Let me get started here. What's happening here? All right, Benjamin. Hit the road. Yes, we see no phone. Very good. Go sit over there. Very good, very good. Excuse me. Goodness gracious. All right. Behave, otherwise I will be forced to pop the swords. Just so you know. All right. There we go. That's a real threat. I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and that we can understand a little bit about your creation. Help us to glorify you. We do this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today we are going to cover what is known as quotient vector space. And so what is quotient vector space, or quotient vector spaces really? This rests on the notion of what's called a coset. Yes, Benjamin?
Why do you put your phone?
Well, Daniel has to have the phone because you're going to go get Matthew in a second. So go sit down. You can't play my phone right now. Sorry. When Daniel gets back, he can have the phone back. So definition, first of all, we can, if we have S and T subsets of some vector space, and then we define S plus T, like how do we add two sets together? By definition, we take elements from both sets and we add them. All right, that's the definition of the addition of two subsets of a vector space. That's how we do that. For one thing, that's our definition. And also, if we were to say X plus S, right, this is X plus, say, little s, such that S is an S, right? And so this right here, what you're doing, and this is for a vector in the vector space, all right? So we can take a vector in the vector space and we can add it to a set, and this, what it does is it just shifts the set over all by that particular vector, whatever it is, right? So a coset is when we do this with respect to the set being a subspace. All right, so if we let like S be a subspace and do this X plus S business, then it's called a coset. Let me define that carefully here. So here's the definition. V, a vector space with W, a subspace of V, then X. Did I ever move the camera over here, Daniel? You moved it, okay. X plus W equals to, again, X plus little w, such that little w is in big W. This is let's see here, is a coset of W. All right. And I should mention that sometimes if we want, we can use a special notation to just summarize this. We could say that this is equal to like bracket with an X inside it, okay? But I'll talk more about what this notation is and why we use that notation in this context. But if I don't want to actually write the W out like that, I could just say it's the coset represented by X. So it's the coset of W with representative x, all right? So let's just look at some examples right quick, yeah? So example 1, if I was to say take W equals to the span of, I don't know, let's say 1, 1, right? Then W is what? It's the line in the plane, right? Y equals x, right? So W itself, I could draw as this red line here. And then what are the cosets? If I take that and I look at like, x naught, y naught plus W, what's that give me? I'll make that one blue about that. So if there's some point, right? Maybe this point right here is the point x naught, y naught, right? Then the coset is going to be like the parallel line that goes through that point. And so the cosets of W, it's a family of parallel lines, so-called parallel translates of the subspace. And you could say that generally speaking, like geometrically x plus W is a parallel translate of W. It's not generally going to be a subspace, right? Because x plus W is not generally going to have the origin in it, right? So it's not a subspace, but it's an awful lot like a subspace, right? Like geometrically, it's pretty much the same thing as a subspace, right? So sometimes these are called affine spaces, like a coset is also sometimes called an affine space on its own right. All right, but you notice that if this, well, anyway, there's not a uniqueness in terms of like the representative, right? There's a lot of different, any point, we could pick any point on this blue line, right? Any other point. If this was another point on this line, say this one, x1, y1, then this would be equal to x1, y1 plus W, right? That would be the same, it would be the same coset. I'm afraid to look what's going on over there. All right.
What's wrong with brushing down? Come on.
I don't know what you just said.
Come on, Ryan. Pick it like a man.
I still don't know what you're talking about. Another example would be something like, this one's kind of more abstract. I could say W is the square matrices such that A transpose equals to A, right? So symmetric matrices. And then in this context, if I was to say look at like B plus W, right? This would be a subset of Rn by n, right? It would be a subset of Rn by n. And it would be in one-to-one correspondence, right? One-to-one correspondence with the set of symmetric matrices each coset would be, right? So that would be another, I can't picture that one, but it's, you could do that. Here's one that's interesting, I think, is if we talk about, let's say, the null space of A, all right, that would be a subspace of, let's say, I'll keep it real, so let's say Rn, right? So that's a subspace, right? And if I was to picture that, I'll do two-dimensional picture because why not? So the null space of A is a what? It's a subspace, right? It goes through the origin, zero's in there. So, generically speaking, I don't know, maybe it's this, just, picturing it. This is the null space of A, right? So if I look at cosets of A, cosets of the null space, what are those? all parallel lines. Now this is a little bit misleading. This right here is x2 all the way up through xn, and this is x1. So this is actually a plane, like a hyperplane. It's a, well, I don't know how big it is actually. This is just a picture. I'm trying to just, you know, have something in front of us to look at. It's not literally a picture of it. Fair enough. If it really was a picture, then what you said would be totally fine. Indeed, that would be parallel lines. Exactly right. But let's just think about it like, what does it mean for equations? So here's a, you know, this right here. If this point is, let's say xp, then xp plus the null space of A, right? That's a coset. What's its significance? Well, let's think about it. So let's see here how to say this. I may need to come back to this example once we've done a little bit more of the theoretical development to get the most out of it. But let me just like, what happens when we multiply A times something in the coset? You know, what if I take A times, you know, let's let x be an element of xp plus the null space of A, right? Then that means that x is equal to what? That means x is equal to xp plus xh, right? Where A times xh is 0. So if I multiply A times x here, I would have A times xp plus xh, where axh is 0. Benjamin, you're really starting to make me question my decision to let you come today. Stay over here.
Don't delete my phone.
Well, the thing is, I am teaching class, and I kind of need to write here. You know? I mean, stopping people from using their phone in class is important, but slightly less important than teaching class. You know, because if all we have is stopping people from using phones, it doesn't really, you know, it doesn't really teach any math, as far as I know. Does it? A little? No. The whole test is just to put your phone away and stare blankly at the whiteboard. All right, so look, of course, this is what? This is equal to AXP plus AXH, but by construction, AXH is 0, right? So we've seen something like this before. If you think back, like, what's the solution set? What is the solution set to a non-homogeneous problem? What's it look like? You know, if I'm solving, say, AX equals to B, then that means I can write x as equal to some xp plus xh, where xh is in the null space of A, right? And A times xp is actually equal to B. So what I'm trying to tell you guys is that, hey, you know, a coset of the null space is exactly the structure of our solution set, right? Our solution set to a non-homogeneous problem is in fact a coset of the null space. We could look at it that way. Yes, Benjamin. I'm starting to think I really should ban you from coming here. All right, well, convince me not to ban you then.
He's just graphing the sine curve.
Sine curve. I don't know what this is, but it is something. What kind of marker are you using? All right, anyway, another example which is near and dear to me is we could be looking at, say, function space from the reals to the reals, let's say. So the set of all functions from R to R. Yeah. And And then I could look at like W equals to, oh, I don't know, Y, let me call this thing V for the sake of not writing it again, Y and V such that dy dx is equal to some given function f, right? And instead of looking at all functions, let's make our life a little bit simpler. Let's just think about continuous functions, right? Or hey, tell you, I'll up it up another notch here. And smooth functions. Why not smooth? Let's be really lazy. Smooth functions. So as many derivatives as you want. So maybe I'm looking at my subspace is the set of all functions that the derivative of the function is equal to another function. What is this? Well, first of all, that's not a subspace, is it? Yeah, my bad. I guess I have to say, well, is it a subspace? Oh, man. Rats. Benjamin, you're not helping me, buddy. Okay.
Wouldn't W just be mean? Aren't all infinitely, or all?
Yeah, this is not what I want. I'm sorry. Yeah, this is not the example I'm trying to create. What I want. Just a second. I need to write something down, and then I'll be able to think of it. That was not it. If you think about well, anyway, maybe the example will come back to me later in class. That's always a problem. So let's go on. So there's a couple of examples of cosets, right? And we can do this for any subspace, all right? And what I want to show you is that there is a way of essentially creating a new vector space where we essentially just squash the subspace. Essentially, in this new vector space, the subspace that we're forming cosets by, we just collapse it to nothingness. So in some sense, it's like a way of dividing by zero, sort of. But I mean, the notation is kind of indicative of division by zero. It's funny. I was just thinking about this. It's not really dividing by zero, but if you took the notation at face value and how we interpret the meaning of the subspace in the quotient, it kind of looks like division by zero. We'll get there in a second. So let's first of all develop some basic things. So one of the first theoretical tidbits we need is, I guess I'll do it here. Proposition 3.76, and it's here. Same context as before, but here's the deal. X plus W is equal to Y plus W if and only if X minus Y is an element of W. So this answers the question in part, how do we judge when two cosets are equal? Well, two cosets are equal if and only if the difference of the representatives is itself in the subspace. So let us prove this. So we'll go this direction, all right? So suppose X plus W is equal to Y plus W, right? Then X plus 0 equals to X is an element of X plus W, as 0 is an element of W, which is a subspace of V, right? So first order of business, since 0 is in the subspace, and the coset is X plus anything in the subspace, that means that the representative itself must be an element of the subspace. All right? So X is an element of W. Excuse me, X is an element of X plus W. But if these sets are equal, X is an element of Y plus the set W, right? Thus, there exists W, let me call it, W in big W, such that x is equal to y plus the little w by the definition of coset, right? And what does that tell me? Well, that tells me that x minus y, tell you what, I'll put a sub 1 on this so it looks a little bit different. That better? There you go. So thus, x minus y is equal to w1, which is an element of w. And that completes the forward implication. If they're equal, the difference must be in the subspace. Okay? And then what? Well, how about the other direction? The other direction is a little bit more annoying because we need to prove set equality. How do you prove equality of sets? Prove that what's in one set is also in the fine. I want to see how far I go, huh? I was about to do it. Man, this board is dirty. All right, so yeah, we need to prove. So Sperano usually calls this what? Double containment, I think. Yeah. So we need to prove double containment. However, given the symmetry of things involved, maybe we'll get away with just showing one direction and then arguing by symmetry or something, perhaps. As much as I hate to bring one direction into anything. But, sorry. It just happens. So the other direction here, we're going to assume x minus y is an element of w, right? Then x minus y is equal to w sub 1, which is some element of w, right? Notice that x plus w is equal to, what is it? It's equal to x plus little w such that w is in w, right? If I could somehow show that that's literally equal to y plus w, then that's another way we could prove this, right? If we could prove they have all the same elements, that's another method of proof. I don't know. Would you guys want me to try double containment, or do you want me to try to show that they have the same elements? Pick your poison?
Let's go with double containment.
Double containment. All right. So I'll erase this. See, because double containment starts with picking an element in one of the sets. So let's let z be an element of x plus w, right? Then z is equal to x plus w2 for some w2 and w, right? Thus, z is equal to, y plus w1 plus w2, since x is equal to y plus w1. So what am I doing? I'm using what I've assumed, right? Here, that gives me this. And I'm swapping the x out for y plus w1. All right, so then thus what? But w1 plus w2 is an element of what? W, right? Thus, y plus w1 plus w2 is an element of y plus w. Which means what? So z is an element of y plus w, right? And so x plus w is a subset of y plus w. We have reached the 50% mark in the double containment proof, right? And I guess there is a slight asymmetry here in that x and y appear slightly differently, right? I mean, x has a plus, y has a minus, but it's pretty much the same proof.
You get x minus w1 instead of plus.
Oh, you're just saying what's going to happen? Yeah. So let me go through it here. So I'll choose a different letter. How about u? Let u be an element of y plus w, right? Then u is equal to y plus, I guess I'm at w3 now, right? w3 for w3 and w. But x minus y equals to w1 implies that y is equal to x minus w1. Hence, u is equal to x minus w1 plus w3. And as minus w1 plus w3 is an element of w, we find that u is an element of x plus w. Therefore, y plus w is a subset of x plus w. So we've showed that's a subset of that, and the other is a subset of, both are subsets of each other. Consequently, we get equality of the cosets. Thus, x plus w equals to y plus w. Yay! Done, right? Any questions?
Was the other way you were going to do it faster?
Maybe. I mean, if you start with x plus w, it is x plus little w, such that little w is an element of the subspace. And then I can trade that x for y plus w1 plus w. And then I just have to argue that since w is free, this ranges over all vectors in the subspace. Therefore, I can just as well write this as y plus, w2, such that w2 is an element of w. I mean, I can just say this equals w2, and there's no restriction on it. And this is equal to y plus w. So yeah, I guess it's quicker. But I might ask you to do the proof by double containment, possibly. I don't know. I might forget and leave this door wide open, I'm not opposed to giving shorter proofs, if they're logical. Do you guys understand this? Does it make sense? Yeah. So that's why they're equal, if the difference is in the subspace. So, yeah. So that is a coset. Now, when is a coset? Let me see here. I think the proof of my notes can be vastly shortened for the next proposition if we just have a little lemma. 0 plus w is equal to w. All right? Do you guys agree? Can you prove it?
As long as W is
I mean, what is this, by definition, this is 0 plus little w, such that little w is in the subspace, right? But that's equal to little w, such that w is in the subspace, which I'm pretty sure is just the subspace, right? So, yeah. So if I know that, my next proposition concerns, like, when is x plus w? The next proposition is like, when is x plus w is equal to w? Right? So that would be equal to 0 plus w by the lemma, if and only if what? X is equal to 0. Nope, not true. Nope, 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 nope.
X is in W because X minus 0.
Right. So logically, using the proposition here, x minus 0 is an element of w, which of course is clearly equivalent to x is in w. Now so this is my proposition 3.77, I think. But I just made the proof like way, way shorter. So my notes are not always logically like, my notes can be improved. Sometimes I'm just doing a proof so you guys have another example of that proof type, not because it's the most logically efficient thing, That's the charitable way to read my notes. The less charitable way is I don't know what I'm doing, so I just did a longer proof. You pick it. But nevertheless, this is true. And it's useful for us to stop and put this in the other notation. See, because what this says is that the set represented by 0 is equal to 0 plus w, which is just w. Right? That's what this means. The coset represented by 0 is the subspace itself. All right. Now, let's see here. So next up, we want to look at what happens when we add cosets, right? The thing I just erased was how we add sets, right? So now we need to use it. So here's the proposition 3.7.9, which says that if you have x1 plus w equals to x2 plus w, right? And you have y1 plus w is equal to y2 plus w, all right? And C is in the field over which we're working, then x1 plus y1 plus w is equal to x2 plus y2 plus w, and cx1 plus w is equal to cx2 plus w. Let me briefly restate this proposition as it looks in the other notation. So in the representative notation, what we're saying is that if we have x1 equals to the coset represented by x1 and x2 are equal, and we have the coset represented by y1 and y2 are equal, then the coset represented by x1 plus x2 is equal to the coset represented by y1 plus y2. Wait a minute, my bad. x1 plus y1 and x2 plus y2. And also the coset cx1 is the same as the coset represented by cx2. So here's the same proposition, but written in the representative notation. I think it's nice to see this. And you see why the representative notation is so nice, right? It's much easier to see what's going on at a glance, isn't it? Yeah. But understand what it means. It's like there's a lot hidden there, isn't there? And the bad thing about this notation is it makes no explicit reference of which coset, which subspace you're basing your cosets off of, right? Okay, so how do we prove these assertions? What's the proof look like? What do you guys think? I say again, what?
It looks a lot like the subspace theorem.
Kind of like the subspace test proof theorem. I mean, kind of, sort of. How about we need to use the proposition over here, right? So, like, let's assume the conditions of the proposition, and I'll look at the proof over here. So we're given that x1 equals to x2, which means that x2 minus x1 is an element of the subspace, right? And also y1 represented and y2 represent the same coset, so that means that the difference is in the subspace, right? And let's be more specific. Thus, there exists, say, W1 and W2 in the subspace such that what? X2 minus X1 is W1, and Y2 minus Y1 is W2, right? And I know where this is going, so let's just solve for x2 and y2 right now. Let's get it over with so we have it to work with as the proof continues, yeah? So this means that x2 is x1 plus w1, and this tells me that y2 is y1 plus w2, right? So what do I need to, I'm trying to show that, x1 plus y1 is the same coset, represents the same coset as the one that's represented by x2 plus y2, right? So that means I need to show that the difference in these guys is in the subspace. So let's do that. If I can find my markers, I keep losing them. All right, so here we go. I bet x2 plus y2 parentheses minus x1 plus y1, right? Let's consider this. That's going to be equal to what? Oh, well, we can put in. I think I'm going in some sort of vicious circle here. I really didn't need to do the blue part, did I? Should I erase that part? Permission to erase the blue part, yeah? Because it doesn't need to be there. We can just use these directly here, right? So this can be rewritten as x2 minus x1 plus y2 minus y1 using commutativity and associativity of vector spaces, right? But that is respectively w2 plus w1 in my language, which of course is an element of w. And let's, okay, fine. If I was lazier, I probably could have done both at the same time. So we got that. And so thus what? X1 plus y1 is equal to x2 plus y2, right? They're the same coset by proposition 3.7.6, right? And if we look at cx2 minus cx1, that's equal to c times x2 minus x1, right? which is equal to CW1, which is, by the way, an element of W. Thus, the coset represented by CX1 is equal to the coset represented by CX2, right? And that's the theorem. There's not really much to prove here, but we do need to check it, okay? Now why? Why do we need to check it? You're right. Otherwise, if this, so this is important because these things we just did, they're going to serve to define the vector space structure on the quotient vector space. So let's define it. Here we go. So here's the definition. V quotient W, the quotient vector space, is the quotient space of V by W, right? And this is, of course, a subspace of V over F, all right? Is the set. So here's what it is, a set. It's a set of cosets. So V by W is equal to X plus W, such that X is in the vector space. All right. And we define addition as a mapping from, you know, the Cartesian product of the quotient vector space to itself, and scalar multiplication, which I'll call dot for the moment, from the quotient of the field, the Cartesian product of the field and the quotient vector space to itself by the following rules. So X plus W plus Y plus W equals to, you guys fill in the blank, and C times X plus W is equal to, you guys fill in the blank for me.
It's going to be X plus Y plus W.
Uh-huh.
CX plus W.
Exactly. I will now remove the line. But there you go. Those are the definitions. And they're reasonable definitions because of the last proposition I proved, right? What do you need for a vector addition? It has to be a function, a single valued assignment from a pair of vectors to another new vector, right? And this is a single thing because it doesn't matter if I pick a different choice of representative over here, right? And they're the same coset, then the output's the same. And likewise down here, if I pick the different representative, it doesn't matter, the output's the same. That's what the previous proposition proves. It proves that these operations are single valued. Now it remains to check the rest of the axioms, right? Associativity, you know, is there a 1, is there a 0, all that jazz, right? But the proofs are pretty straightforward from this point, now that we have motivated you know, the logical foundation of the coset. I guess you could say calculus, but you know, arithmetic maybe is a better word here. What's 0? So what's the 0? So there has to be a 0, right? So like, check it out. 0 plus W, right? Plus X plus W, how's that go? 0 plus X, right? Plus W, which is X plus W. In other words, this is, of course, W. So W itself plays the role of 0 in the quotient space. Quotient space is something really creative and new. We're not just taking the vector space we already have and doing something really simple with it. We're taking what we have and we're replacing the objects with new objects, right? Instead of thinking about points, we're thinking about, you know, perhaps lines or planes collectively as a point in the new space. So in like the quotient vector space of the first example I gave with the set of parallel lines, every one of those lines is a point in the quotient vector space. So the subspace just becomes a point. And that's why I was kind of making a joke about division by 0, because the notation is like dividing by w, and we're squashing it to 0. That is what it is here, right? But this is, you know, truthfully, this is not a multiplicative coset, right? So I don't know, it's kind of more like you're subtracting w out. Anyway, you're squashing w to 0 in the sense of what this thing is. The example I was trying to think of earlier had concerned with the, basically what I was trying to think of, guys, was like the kernel of the derivative operator. And we'll talk more about this next time, but the kernel of the derivative operator is a subspace of the smooth functions, right? What is that subspace? It's what?
That's just,
What is the kernel of the derivative operator? Yeah.
is that just all constant?
All constant functions, right? So if I look at the coset, if I look at, you know, smooth functions, right? Mod the kernel of the derivative operator, right? What do I have in here? What do my cosets look like, you know? I've got representatives of, you know, some, you know, a coset represented by this function, let's say, you know? And what does it mean for two cosets to be equal in this context? What does that mean? That's true if and only if what? The difference is in the kernel of the differentiation operator, right? Which is tantamount to saying what? F minus g is equal to a constant, right? Which is tantamount to saying that f of x is equal to g of x plus a constant for all x in the reals, right? So that's what the coset looks like with respect to the subspace of the kernel of the differentiation operator. Have you ever worked with this before? Surely?
Integrals.
Integrals, that's right. When we write the integral of x dx is 1/2 x squared plus a constant, what we really mean is the set of 1/2 x squared plus a constant such that the constant is a real number, right? It is actually a set of functions, all of which differ at most by a constant. Every antiderivative, every indefinite integral you've ever done, you've been assigning a coset with respect to this notion of equivalence. By the way, there's a coset equivalence. 2 points in the vector space are equivalent if and only if they lie in the same coset. That defines an equivalence relation. These cosets partition the space. You could kind of see that in my earlier examples as well, right? There's a subspace, and then you've got affine translates of it, right? Every point is in just one of those, right? Anyway, we have much more to talk about in terms of structure here. And next time we will learn the first isomorphism theorem, which I have several homework problems about in your next homework. Do not be scared of these homework problems. They are gifts. Because once we prove the first isomorphism theorem, those homework problems are very, very simple. First isomorphism theorem is the laziest and most fun way to create isomorphisms. All right? So, in any event, have a good weekend, you guys.